We're given a globe now, and this has a diameter of 12 inches, and it fits inside of a cubed-shaped box that has a side length of 12 inches. What is the volume, rounded to the nearest hundredth of a cubic inch, of the space inside the box that is not taken up? So let's try to draw a picture here, a very rough sketch picture. We have some box here, and then we are going to take some sphere. Like I said, very, very rough drawing. And when I take this sphere, I am now trying to put it inside of the box so that when it sits inside of the box, we are looking for all of the unused space. So everything around these corners, all of this unused space around here. We are trying to figure out what is that answer. So, since the box is larger, we are going to find the volume of the box first. And now we are told that the side lengths of this cube, and remember, if it's a cube, that means that it's made up of squares, so every side length is 12. And then we're also told that the sphere has a radius of 12 as well. So the volume of a box is just area of the base, which would be 12 times 12, times your height, which is also 12. So this equals 1,728. And then I'm going to switch to red to find the volume of the sphere, which is 4/3 pi r cubed. Now we are given the diameter, but we need to find the radius. So I would just split that in half, and half of 12 is 6. So my radius is 6, and I'm going to cube that to get me 904.779. So now to find our unused space, we're going to take the cube volume and then subtract the sphere volume from the cube. And when I do that, I end up with 823.221. Let's double check our units. It was inches, so this would be inches cubed. So this is all of the unused space inside the box. So maybe you could put, if you were maybe shipping this globe somewhere, you're sending it to grandma far, far away, got to really pack it nice. We're going to put a bunch of packing peanuts in there, make sure it's secure. Okay, now this next question, remember these are sample state test questions. So saying what three-dimensional figure could result from rotating the square 360 degrees about the y-axis? So we are taking this square, we are going to rotate it all the way around this y-axis. Remember, the y-axis goes up and down. That is what I've highlighted. Well, as I kind of drew that picture, we see that it's going to have some type of circular shape. So right off the bat, we can get rid of those pieces there. Now we have an option. Is there going to be a square in the middle, or is it going to be a circle in the middle? Well, let's focus on point J here. If I rotated point J around this 360 degrees, I end up with a circular shape. So I can almost solve this problem just by drawing the visualizations to realize that this is going to be answer A. Okay, moving on to density. Density is simply a ratio of two measurements. Typically, we use the formula D equals M over V, or mass over volume. We can also talk about population density, so like how many people can fit in a certain area of land. Think about your classrooms. It wouldn't be practical to say we could fit 1 million people in a classroom at Darby High School. We have to have some sort of population density. So here is some more state test questions. A study reports that in 2010, the population of the United States was 308,745,876 people. And the Lang area was approximately 3,531,087 square miles. So we're given some land area here. I believe this was a typo. And we're given a population. So what is the population in people per square mile of the United States in 2010? So we take the number of people, which was this really, really big number, and we just simply divide it by the area of the land, which is 3,531,087. And when you do that, we end up with 87.4. Remember, this is telling us people per square mile. So basically, this is saying that in 2010, there was 87.4 people per square mile. Now, we know that you can't really have 0.4 of a person, but the question was asking for us to round to the nearest tenth. Okay, so my homeboy Jeremy, he wanted to know the density of a rock in grams per cubic centimeter. So this rock has a mass of 1.4 kilograms and a volume of 400 cubic centimeters. So what is the density of the rock in grams per cubic centimeter? This is very, very important, because we may not know right off the bat which one is going to go on top, which one is going to go on bottom. So we go back to our problem. We say, do we have something in grams? Well, we have a mass, and remember the equation is m over v, but that is in kilograms. So we are actually going to have to convert from kilograms to grams. So if we have 1.4 kilograms, your conversion is that there are 1,000 grams in 1 kilogram. So 1.4 kilograms is actually 1,400 grams. So we had to do a little back work there. Now, do I have centimeters cubed? You bet that I do. So now we have our mass, which was 1,400, and our cubic centimeters of a volume, which was 400. So 3.5, and then remember this was grams over centimeter cubed. So that one had a little extra work we had to do to get our desired answer. Okay, throwing it back to some similar figures here. Similar figures have the same shape, but different size. So I gave you two rectangles here that are similar, and we want to find the scale factor going from the small rectangle to the large rectangle. So since we are getting bigger here, we know that our k value is going to be greater than 1. So I'm just going to pick 15 and 10 here. So k equals 15 over 10, which that simplifies down to 3 over 2. So we found the k value. Part 2 here says, determine the perimeter and area of each rectangle. So the small, since these are rectangles, we know that this is also going to be 16. and this side is also going to be 10. So perimeter equals 16 plus 10 plus 16 plus 10, which equals 52. The area is simply base times height, so 16 times 10, which is 160. Now for the large rectangle. So the perimeter of a large rectangle would be 15 plus 24 plus 15 plus 24, which equals 78. And then the area, base times height, 15 times 24 equals 360. So continuing on further, find the ratio between the perimeters and the areas. So the perimeter of the large was 78, the perimeter of the small was 52. When I simplify this down, this also equals 3 over 2. Now, for the area is 360 over 160, which that equals 9 over 4. So finding some ratios, and how does this compare to the scale factor? Well, the perimeter, that's just the same. The area is 3 over 2, our k value, squared. So when you square something, it goes onto both. So 3 squared is 9, 2 squared is 4. So if area is terms of squares, now we're saying, how do you think the volumes of similar solids would compare? Remember, we write volume in units cubed. So you would just take your k value and cube it.